If the net force acting on an object is 0, if that's 0, its momentum is conserved. What does that mean? That means the final momentum will equal the initial momentum if the net force is 0. Let's take an example. Figure skaters. Sometimes you watch figure skaters, and I use figure skater because I'm looking at their blades and ice. I'm assuming there's no friction. That's the closest no friction for us. We have a couple of figure skaters. Here we go, doing their routine. And they stand in the middle of the ice, and again, neglect the friction between the ice and their skates. If they want to go in opposite direction, what do? They push their hands together. The couple push on each other, toward each other. So this person is pushing that way, this person is pushing that way. What's going to happen that this skater will go backward, and this one will go backward with different speed, unless they have the same mass. If the mass is the same, they'll go backward with the same speed. But let's give the male skater a mass of 85 kilogram, and let's give the female skater a mass of 70 kilogram. So their masses are not the same. Somebody noticed that the male skater is going backward with a velocity of 2 meters per second. The question, what's the velocity of this female skater? How fast is she moving backward? Okay, let's look at the final. Initially, they were standing, looking at each other, touching each other's hand, no pushes, nothing. So initially, their linear momentum was what? 0. None of them was moving. So the male skater is 85 kilogram times the initial velocity, which is 0. Add to it the female skater, the mass is 70 kilogram, initial velocity was 0. They weren't moving. They pushed against each other, just like if I push on this table. Notice I moved backward and the table moved backward. Same thing. Now let's look at the after they start moving. I'm going to use to the right is positive, to the left is negative. So this one, the male skater will have a momentum of 85 times the velocity, which is 2. The female skater will have a mass of 70. And if I know she's going to the left, I can say negative, and the value of her speed is v. We're looking for it. It's negative because it's going to the left. If you don't know what's going to happen, you can just put v, and your number will be a negative number. We'll let you know it's going to the left. But if you know you're going to the left, you put the minus, and the number you're going to get, the v, is just the speed, the value of that. We know it's going that direction. This is 170 minus 70v equals to 0. 170 equals what? 70 v. Can we get the velocity? .43. Bless you. Meters per second. And again, the value is 2.43, the direction to the left, because I already drew an arrow going to the left. But the value of that speed is 2.43. Notice here the two objects are not moving, they're not colliding together. Now, if you want to start thinking about a hockey player going toward a player, hitting a player, that's a different story. That's collision. Still in the same area we're talking about. But the question becomes, is it elastic or inelastic collision? So we're going to use conservation of linear momentum in both cases. So the next topic, which is elastic and inelastic collision, is actually a continuation of this one. So let's talk about inelastic collision. Inelastic. What's inelastic? We'll use a football player. We have 100-kilogram football player running in this direction, going after the quarterback, moving at a speed here, velocity of 3 meters per second. Tackles a quarterback. This is the quarterback. The mass is usually lighter here. We'll say 80 kilogram. It's not moving. And when he tackles that quarterback, he holds him. This is the before. And after that, the two of them, actually I should throw it down. The two of them laying on the ground because he tackles him. He's holding him. They got stuck together and they fall down on the ground. And the question, after he tackles him, what was the velocity before they hit the ground? What was the velocity of the two of them stuck together? Stuck together. This type of collision is called inelastic collision. When they stick together, it's called inelastic collision. When you have inelastic collision, we have no net forces. Notice the only force we have, this person, this defensive player, hitting the quarterback. He's going to hit the quarterback with the force. Well, the quarterback is going to push back with the same force. So there's no net forces acting on that. We have conservation of linear momentum. Anytime you have inelastic collision, you will have conservation of linear momentum every single time. Which means the initial linear momentum should equal the final linear momentum. Now let's look at the initial linear momentum. That's before the collision, before they hit each other. We'll talk about the defensive player here. the cornerback, the safety, pass rusher, whoever that player is, has a mass of 100, moving in this direction with a speed of 3. Mass times velocity is what linear momentum is. The quarterback has a mass of 80, bless you, was not moving, 0. Should equal, what's the combined mass? Now, I gave you a hint there. Once they collide, he runs to him, he grabs him, stick together. So we have a combined mass. And the combined mass for them should be what? 100 plus the 80. And they're going to move with some velocity, which is we're looking for it. They're going to move together with the speed. What's that speed equal to? Well, we got 300 here equals 180 V. V equals what? .7 meter per second. So the two of them will be moving at a speed of 1.7 meters per second. We'll do a couple more inelastic collisions. They're straightforward. Conservation of linear momentum. If you ever seen a train and this is the train here, and you want to add this one to it. So they push this one, so this will be moved. This is not moving, has a velocity equals to 0. And let's say the mass here is 10,000 kilogram. You bring this cart. This is moving. Let's say the mass of this is 2,000 kilogram. Moving at a velocity of 5 meters per second. Once it touches this, sticks to it, couples together. There's a little hook. They stick together and they're going to move together after that. So this is the before. After that, you're going to see the three of them stuck together. And what's the velocity after? So this is the after. This is the before. So the before, this was not moving. Only this one's moving. This one hits it. The whole train, all of these going to move now with some speed. Again, the fact they stick together is called inelastic collision. You're going to neglect that sound that you hear when they hit. Why we neglect the sound? Because if you don't neglect that sound, we have energy lost there. So we don't have conservation of, really, net force is 0, conservation of kinetic. By the way, kinetic energy is not conserved when you have inelastic collision. If you do 1/2 mv squared before and after, they will not equal to each other. So let's look at the before. The mass of this, which is what? 2,000, not 2 kilogram. I never saw a train cart only 2 kilogram. 2,000 kilogram. So the mass is 2,000. Velocity is 5. Plus the 10,000 has a velocity of 0. Equals. The combined mass, they stick together. The after is 12,000 times the velocity, which is unknown. it's 0.83. So after this one collides with that and stick together, the entire train will start to move forward of a speed of 0.83 meters per second. Where this becomes really tricky when we start dealing with two dimension. Then we got a little problem there. Just to give you an idea, I have something for you for the lab on, not tomorrow, but next Tuesday. Remember when we did that experiment, that projectile, those guns, we fired that silver ball? Well, we're going to do the same thing, but this time, what's going to happen is we're going to fire the ball. The ball's going to come hit this one, go inside that, then it's going to swing up there. And we need to know how high is it going to go. If you imagine you have a block of wood attached to a string dangling from the ceiling, and we're not going to take a gun and shoot somebody. You take a bow and arrow and you hit the block of wood. Now the arrow goes inside the wood, sticks inside it. Now both of them start to rise up there like pendulum. And how high would it go? First, I need to know the masses of these two. I'll give you some numbers. Anyone recall what the mass of that ball was? Did you ever weigh the mass of that ball? That wasn't small. Let's say, I don't know, we'll just use 40 grams. That's this guy. That piece probably has a mass of half a kilogram or 500 gram, that block there. So this is what we're looking at. We got a ball, and if you remember in the lab, your velocity was roughly, this is 0.040 kilogram. If you remember from the lab, your velocity was around 6. Some of you got 6.1, 6.15. Remember that one? So move in with the speed of 6 meters per second. There's a block sitting right here. The block has a mass of 500 grams, which is 0.5 kilogram. Has a velocity equals to 0. This is the before. Right after that, the ball goes inside that. Actually hollow, the one we have there. And the ball goes inside, and we have a little spring that closes the trap, the door, and the ball can't fall out. So now the ball is inside that. What's the combined mass? Notice this is inelastic collision. The ball goes, sticks with it. So what's the mass now? 0.54 kilogram. The sum of the two masses. And what was the velocity here? So that's what you're going to do in the lab. So make sure you want to write that up. So when we go to the lab, that's next Tuesday. So what was that velocity there? We have inelastic collision. They stick together. And when I hear inelastic, I know we have conservation of linear momentum. If it's conservation of linear momentum, I know the initial linear momentum should equal the final linear momentum. The initial is what? The mass of the ball, which is 0.04, times the velocity of the ball, which is 6. Add to it the mass of the block here, which is 0.5, times the velocity, which is 0, equals the combined mass times the velocity v. 0.24 equals 0.54 times v. Can we get v? The speed is 0.44. I'm not looking for this velocity here. That's just part of the problem. What's going to happen in the second part, once that ball goes inside that block there, so this is the second half of the story. The ball enters the block right here. So we know this block has a mass right now, 0.54, and it's moving with the velocity of 0.44. We just calculated that number. Right there. The string is attached to the ceiling, so it doesn't move. So that block is going to move right there. And the final velocity here will be 0. And the question is, how high is it going to rise? What's the height? In our lab, that height is about 6-7 millimeters. Well, not millimeters, about 6-7 centimeters. So it's not much, about this much. Well, how do we calculate how high does it go? There's no more collision. We go back to chapter 8. Conservation of mechanical energy. If we neglect the wind, if I neglect the wind and the friction, neglect friction, then I have conservation of mechanical energy. I'm putting the two chapters together now. We'll call this 1, position 1. This is position 2. The mechanical energy at position 1 should equal the mechanical energy at position 2. What's the mechanical energy at 1? It's the kinetic energy at 1 plus the potential energy at 1. 2 is the kinetic energy at 2 plus the potential energy at 2. Now, never mind the ball by itself. So what you're looking at, this is the story now. The other story is gone, history. We get all of these together, moving at that velocity. We're going to rise to this one. If I use this initial height here as reference, the kinetic energy is what? 1/2 the mass, which is 0.54. What was the initial velocity of these two combined? 0.44? Add to it the potential energy. What was the potential energy? The mass, which is 0.54, gravity, which is what? 9.8, times the height. What was the initial height from this line? What was that height from here? 0, yes, is equal to, let's look at the kinetic energy up there. 1/2 the mass, which is 0.54. And what was the final velocity at the top here? 0, and square it, still 0. Plus the potential energy, which is what? The mass, 0.54, times gravity, which is 9.8, times the height, h. This is 0. That one's 0. Point 0.5 times 0.54 times 0.44 squared is 0.052 equals 0.54 times 9.8, 5.29 H. Can we get what H is? 0.052 divided by 5.29, which is 0.01 meter. So based on the numbers I gave you, it's going to rise 1 centimeter. That block, again, I made up some numbers. That block will go up 1 centimeter high. Swings. Not that high. So notice I'm combining here. Once I neglect friction, I'm combining chapter 8 with chapter 9. Conservation of linear momentum, conservation of mechanical energy. Both of these examples that I did, both of them, we were moving in one dimension. We were moving left to right. Notice they tackle straight forward. Well, that's not always the case. Let's give you a story here, a scenario. You're approaching an intersection. So this is an intersection. Oh, somebody's happy. There's a car coming in this direction at, we'll say it's going this direction of velocity equals, 20 miles per hour. Not too fast. Has a mass equals 1,000 kilogram. And there's a car coming from here. Velocity for this is 25 miles per hour. The mass is 1,200 kilogram. Neither one slows down. They collide and they stick together. Well, when they stick together, they're going to move. Here's the two cars stuck together, and they're probably going to go in that direction. I'm drawing the picture like they're stuck together, and they're going to move in that direction. They collide, and they're going to get off the road and go in that direction. And the question is, can you tell me what is their final speed and the direction? What's theta? Like if I measure theta here, can you tell me what that value is? What is v and what's theta? So this is actually a two-dimensional collision, inelastic collision. They stick together and they're going to move in that direction. Again, the fact they're stuck together, we have inelastic collision. Which means conservation of linear momentum. Let me draw these a little bit nicer. Instead of cars and everything, I just draw pictures there. So here's what I know. This is car number 1. It has a mass of, I'll just use a dot for that, has a mass of 1,000 kilogram, and it's moving with the velocity of what? I got to convert that from miles per hour to meters per second. 20 divided by 2.24. 8.92 or 8.93 meters per second. I got another one coming down. It has a mass of 1,200. Velocity is convert the 25. 25 divided by 2.24. 11.2 meters per second. They're going to collide here. Here's the two cars stuck together. And they're going to move together in this direction. We'll call that V final. I have no idea what that number, I'm looking for it. And I'm looking for that angle. That's what I'm trying to find. What is V and what's theta? Make sense? Picture? We said we have conservation of linear momentum here. I just wanted to clean that picture and make it look like this. Since I'm moving in 2 dimensions, I have to look at it in each dimension. I got to look at it in the x direction and in the y direction. The linear momentum before in the x direction should equal the final momentum in the x direction. And I also got to look at the y direction. The linear momentum in the y direction, initial one, should equal the final one in the y direction. This is before they collide, right there. See the two cars coming? Let's look at this. In the x direction, what's the linear momentum for this? It's the mass times the velocity. What's the velocity of this in the x direction? 8.93. Plus the other car, 1,200. What is the velocity in the x direction for this car? 0, yes. It's not moving, it's moving the y direction. No movement in the x direction. They collide and stick together. They become one object now. And what's the mass of that object? 2,200. The two cars stuck together. And what's the velocity? What's the velocity in this direction?
8.93.
Not going to be? If this is V, what portion of that in that direction? V cosine theta. That's the velocity in this direction. Eight, 9, 3, 0 equals 2,200 V cosine theta. Divide by 2,200, 8,930, divided by 2,200, 4.06. Now let's look at the y direction. Now we'll take that 1,000 here, that car. What was the velocity in the y direction? 0. Good. Let's look at this car, 1,200. What was the velocity in the y direction? I'm using up is positive, down is negative. Negative 11.2 equals the combined mass, which is what? 2,200, and times the velocity, which is what? V sine theta. Now, I don't know what theta is. I'm taking a guess they're going to move in this direction. A wild guess. They could be moving up. The math is going to tell me. If theta ends up being a negative number, yes, it's moving, that's in the x direction, because this is my axis right now. So if theta is negative, oh yes, should be negative here. So let's do the math. Negative 13,440 equals 2,200 V sine theta. Divide by 2,200. $6.1. And now I have two equations by two unknowns. Two equations by two unknowns. We need to solve them. Let's try. How do we solve them? We can use substitution, anything you want to. So let me write the two equations. V cosine theta equals 4.06. V sine theta equals what? Negative 6.1. I'm going to solve them any way you want to. So let's take this one. We can say V equals what? If you do a substitution, 4.0, not substitution, I'm going with substitution, the method I'm going to use. So first I got to solve for V, or theta. Would be easier if I solve for V here. V equals 4.06 divided by cosine theta. Now let's go to this method and do this equation and do a substitution. When you divide sine by cosine, what do you have? Who took trig? What's sine over cosine? Tangent, yes. To solve, we divide both sides by 4.06. 6.1 divided by 4.06. I got a negative 1.50. To get theta, we do the inverse tangent now of negative 1.50. And it says negative 56 degrees, 56.3. Negative means below the axis. My picture is correct. I made the assumption they're coming down. It looks like I was right, my assumption. It's going to be down 56 degrees. Can we get V? Once I have what theta is, go back to this equation. V equals what? 4.06 divided by the cosine of negative 56.3. The velocity is 7.33. Or the speed. So the two cars will stick together based on my picture, and they will move in this direction at a speed of 7.33. The direction is negative 56. That's how we have to handle a two-dimension when you have things that move in two-dimension. God help us if the two cars don't stick together. It becomes elastic collision. That's next class tomorrow. In elastic, we have two equations for each one, so you'll have 4 equations by 4 unknowns. Because we have conservation of linear momentum and conservation of kinetic energy when you have elastic collision. That's tomorrow. So I'm going to